Super briefly about myself. So yes, as Marius already said, I'm originally from Germany. I have been in Australia for about 14 years now. I am now at Monash University. Monash University is a rather big university, about 85,000 students in Australia, the largest one. And as a consequence of being the largest one, we actually can do a lot of work. A lot of work here, a lot of work there, because we do have a lot of academics as well. And in the next, well, in total about 55 minutes, but minus Q&A, of course, I'll outline some of the projects, well, a very few, that we are working on in the greater space of machine learning energy I should say. I don't have any technology for you, I just have questions for you, maybe some interesting research questions, in case you think, hey, you're looking for a great application, I may have a couple for you here. By the way, maybe before I go further, you'll probably witness some of the worst slides you've ever seen. One of the reasons for this is I've had a major data loss, and yeah, I had to cobble together everything on relatively short notice. So I will probably say many things that are not on the slides, and vice versa. There will be many things on the slides that I won't be talking to. Just follow along to what I say. I will outline a few important things here and there. Do not try to read everything that's on the slides. We'll start here with this one right away. Essentially, so why do we do IT in energy at Monash? I'm not an engineer. I'm not an electrical engineer. I'm not developing the next battery or so, but I can do, and my colleagues, we can help with decision support. Lots of optimization, lots of machine learning models here, left and right. Lots and lots of opportunities there. In the faculty of IT, so we have maybe a dozen or so academics, so that's professors of sorts, so not postdocs, that work in the greater energy space from time to time in IT, in addition to our engineering colleagues, in addition to the business and economics people. We do essentially everything here on the right-hand side, from engaging with individual users, so communicating how we use energy, to, so that's engaging with the humans. And I'll be talking about one project at the very end, maybe for about 5 to 10 minutes in that space. We have some people working on infrastructure. So single building control, single wind farm design, single wind farm operation, single wind farm prediction, output prediction, for example, based on weather. We've got people focusing very much on batteries, so batteries in the sense of community batteries, so batteries being somewhere in the suburb and then people feeding in and taking energy out of it again. We've got quite a number of people working on EVs, vehicle to grid, for example, scheduling, how to distribute facilities, and so on. Once you put a couple of these batteries and buildings together, you end up with precincts or suburbs or cities. So we're looking, some of us are looking into integration of various utilities, and another sub-team of ours looks into national level infrastructure planning, so multi-billion-dollar investments over the next 10, 20, 30 years. Where do you have to build transmission lines, a large-scale battery here, a wind farm there, in order to keep the lights on? Monash itself, so it's not just academics that are happy to work in that space, but Monash itself has made quite a large commitment to, to being net zero, positive at some point. It won an award it got an award from the United Nations at some point. It invests itself about, so in euros, about 80 million euros or so into net zero, into the transition. And it works with many, many large consortia in Australia. Energy is a big topic, as is mining and a few other things, food, but energy is a really hot topic there. That's all I want to say here at the moment about the super high-level outline of all the things that we do or that we are involved with in the Faculty of IT. Right, so very briefly, I run you through 3 cases, 3 examples of what we do. And at the very end of each case, I think I have a couple of maybe some interesting challenges for you if you want to. So, example 1. At Monash University, we unfortunately spend a lot of energy, or we spend a lot of money on heating and cooling buildings. This is not drawn to scale, but if you assume that this is roughly, whatever that means, that is Monash University's overall energy consumption, there's a plan to save a huge chunk through just heating and cooling more efficiently. There is some attempt to, or there's some intention to save a little bit more through replacing lighting. And what is lights? Yeah, some lights and appliance upgrades. And the rest, whatever we can't reduce anymore, we hope to cover through on-site renewables, so lots of solar, and through a contract with a particular wind farm. That's the long-term plan. That's what Monash University wants to achieve. All right. One of the challenges here is, of course, okay, how do you reduce it by this much? How do we get there? Well, one of the great things is, so on the previous slide, this was just a summary over, maybe aggregated over many, many years. But that's can be slightly misleading because you've got lots of temporarily high resolution events. So you have days, right? You've got buildings that you heat up, maybe in the mornings, and then you can wait for the building to cool down slowly, or maybe you have to heat them up several times in winter. And then overnight, you don't have to heat them up anymore because nobody's there. So there's an opportunity to shift some of the overall consumption, maybe to the morning or to the evening. The shifting has several advantages. It allows us to push our overall, demands down. Why is this important? Well, the grid locally has certain capacity constraints. You cannot always just heat everything at once. No, you have to plan ahead a little bit, because otherwise the grid operator says, no, Monash University, you can't turn your heaters on. We're at maximum capacity. You might think that's a bit contrived. No, with more and more households in Australia moving over from gas heating to electric heating, we do put the grid under additional pressure. Yeah. So, lots of text again. What we want to achieve is we want to control our buildings more intelligently. And you'd be surprised that the buildings themselves, they don't do this. Yes, they do have some building management systems, building automation systems from Honeywell, from Siemens or Schneider Electric already built in. But they get set up once when the building is commissioned, and somebody cuts the whatever rope, and then all the students rush in, and then it's forgotten, and 10 years later, for the next 10 years, nobody checks it. So it gets set up once, independent of seasons, independent of occupancy. The way it heats and cools itself, never adjusted normally. We think we can do better. But one of the questions is, how much can we actually get out of this? Through retrofitting, making the controller smarter. We're not touching any of the ventilation, we're not upgrading any hardware, no, just through looking ahead. Model predictive control. So we're after something really, really simple. And for that, we want to exploit that, hey, we can heat up the building in the morning, for example, or at a time when it's convenient. Maybe prices are very low. And then the cost, so we can benefit from this. That's a big, yeah. Now, of course, we can save for ourselves a lot of electricity, money. That's a good starting point. But also for the grid itself, it can have a massive advantage. If we can, across Australia, save gigawatts and gigawatts of electricity, this also means we don't have to build certain batteries in gigawatts and gigawatts in the first place to absorb this. So that's a nice side effect, right? If you consider all the buildings, I know there's a bit visionary thinking here, but if we could schedule, control every single building heating and cooling, we don't have to over-provision essentially. That's a nice idea. And with buildings maybe making up about 40% of the actual energy usage, that's a substantial amount. That's lots and lots of gigawatt hours every year. All right, but we have to find out. We don't know what this gap is, right? It might be $1 that we can save a day or $100,000. Good. So how do we go about this? Well, let's first have a look at some real data. There's a lot happening, sorry. What's shown here in this graph from left to right is, I think, about 1 day's worth of data. There's a lot happening. I'll highlight 2 things for you. This blue line here, at the top, the dark shaded area, that's the production of a wind farm that Monash works with. Exclusive contract and says, you produce energy for us. Okay, whatever, 2.5, what is it, megawatt maybe, and then it goes down during the middle of the day. That's very unfortunate. And then it goes up again. Second line that I want to highlight is the, where do I have it? The light pink one or turquoise one here, cyan, whatever you might want to call this. This is the actual energy consumption average over lots of buildings. Well, somewhat lots of buildings. It's not so high at night. See, there's nothing very intelligent happening. During the day, what is it here? 12 p.m., 1 p.m., 2 p.m., 3 p.m., 4 p.m. It's quite high, and then it trails off again. Now the cool part is, I think in principle, this red area. This red area is meant to be the difference between what we need and what our wind farm produces. Now that's a pretty shit situation, if you ask me, because it means the wind farm is not producing when we need it. But it did produce something 3-4 hours prior to that. So it's a missed opportunity. If we could shift some of the heating or cooling over to an earlier time when we actually produce lots of wind energy, That's fantastic. Free. Everybody wins, well, or at least very low cost. Because these things here during the day, they might suddenly cost a lot. So that's the basic idea here, right? Know when something is cheap or affordable and shift your consumption around. Very simple. One more thing, and I'm not quite sure, maybe some of you work in companies that have, where you know of such contracts. As an end user, normally, I get billed, okay, it really depends. I get billed for my consumption, just one lump sum. I pay, whatever, 35 cents per kilowatt hour. Every single hour. It doesn't matter whether I do it in the morning or evening or late at night. There are some tariffs out there when you buy electricity from E.ON or RWE or whatever it is here. You have some tariff in the morning, some at noon, and some in the evening. There are also for large clients, like maybe universities, they have tariffs that say, okay, if you end up consuming more than this, in this case here, what is it, whatever, 800 kilowatts for a large building, if that building exceeds 800 kilowatts, you're violating the contract and you get a big fine. This is massive. This little blip here, sorry, I had to remove this here, over $10,000 fine. Just for exceeding for one spike. Horrible. Why not try to predict this, right? And then you shift your loads around, save a lot of money. One building. A rather large building, sure. We did the numbers. I'm sorry, I cannot mention anything, also because it's not getting recorded. But let this just be an indication of what can be saved. Okay, so there's apparently two-digit million dollars that we can save with model predictive control, and it costs, because the company that's involved costs also some money. But it's still, nevertheless, over a couple of years or 20 years, I know you don't see the numbers really, but it's millions and millions of dollars saved to the university just with a little bit of software. That's cool. I like this. Now, one reason why I like this is we are trying to convince the university to take some share of this, let's say the first digit off, and the rest we get to feed back into research. Because if we save the university, let's say, $50 million, okay, maybe not, don't cut the first digit off, that was silly. If we save the university $50 million, why not invest $5 million again into research? Everybody's happy, right? No. How did we get to these numbers? Now, building control is nothing new. It has been around for many years. But the state of the art is surprisingly simple. So we weren't very, very excited when we saw this. So when you want to do building control, you have to make lots of decisions. What do you want to model? Luckily, there are some good softwares out there like AutoML Plus and OpenStudio that allow you to create. So this is a simplified model of our building. It lets you create a thermal model of your building. Because you heat the building up, it dissipates energy, it dissipates heat again. But what also happens to the building is as the sun radiates onto the building, it also heats up. So you have to consider that a little bit as well. You have to consider what's the temperature, humidity, and a couple of other things. But how many of these variables do you actually consider then? How many do you follow? What kind of other factors do you consider? So occupancy, where do you get the occupancy data from in the first place? Do you have seasonal effects? So from your Monday, you probably don't want to extrapolate to a Saturday when nobody's on campus anymore. Okay, so that's within a week. Maybe the summer semester is always bigger than there are more students involved than in the winter semester, and so on. So these things. What else do we have? The actual weather. Yes, so what do we want to consider? So we have a lot of input parameters that we have to play with, and ahead of time, you don't really know what's important. The alternative is, of course, that we just throw everything at it, and then you end up with maybe 100 input parameters, and your poor machine learning model will say, look, it's too much, I'll take forever. So some clever approaches here to select the useful one, the interesting ones are quite helpful, are quite important. We don't really know how to do this properly, so parameter or feature selection here will be quite important. Once we build the model, then we need some, well, ideally, we were aiming for some reinforcement learning approach that we could deploy here, and it learns from its conditions. It reacts to the environment. It gets the feedback immediately, of course, well, somewhat immediately from the building. You do have maybe a bit of trouble with the credit assignment problem, where well, you do something now, and because there's a lot of thermal inertia throughout the building, it might actually take an hour or 2 hours for something to, well, go into effect or trail off completely. So structural-wise, there's some interesting challenges here for machine learning approaches. Yeah, and maybe one more thing here is, what do we actually want to optimize? Do we want to optimize for dollars? Do we want to optimize for CO2 footprint? Because depending on the time of day and depending on where you get the electricity from, sometimes it's this really dirty coal electricity during certain times of the day. But if it's today very sunny, it's relatively clean CO2. And this is important because, at least in Australia, universities start to count their CO2 emissions. Yep. So some challenges here. Sorry. In addition to all of this, prices change dynamically as well throughout the day. You may have, well, in principle, the market in Australia clears every 5 minutes, so you have 12 times 24, potentially 12 times 24 different prices throughout the day. So you'll have to predict weather, you have to predict occupancy, weather, occupancy, price, and maybe a whole bunch of other things. And your building model itself should be good to begin with, should be calibrated. What are maybe some interesting AutoML questions? So again, I'm not coming to you with technology or cool packages that you could implement or cool functions to optimize. We'd love to have something that at a press of a button, I know I'm a bit naive here, it tells us, okay, these are the actually important variables. This is how we fine-tune our building model. What else? Yeah. How do we deal with all these different models that predict occupancy, weather, price, and so on? Are they all completely disjunct, I guess, or discrete models? So you have independent models, or do we somehow mesh them all together? I do not know. What we do have is we have this large set of all this, this input data with gaps, unfortunately, here and there, and not necessarily always perfectly synchronized. And we'd like to save electricity or create or use less CO2, but it's not that trivial. In principle, a well-understood problem in the sense that we know what variables we put in, and we want to minimize it in the end, but an enormous tool chain that all has to work together. So I think it was maybe Matthias who said that structural evolution or something along these lines, maybe that is helpful here to put together this large system in the first place. I don't know, just a thought. What else do we have? Anomalies. That could be something really interesting for some people to work on. Maybe some hardware, so that's a little bit independent of detecting whether something is broken or not. Maybe you want to detect whether in a time series a piece of equipment is broken. Now, there's apparently some, what was it? Let me call it, it's just, what was it, auto glue on time series or so, or other packages. So we'll be looking into this, and at some point we also have some machine learning experts for time series, but I think this is an interesting, maybe even a business opportunity for some of you, depending on how the energy tariffs are set up here, where you can predict, okay, either some hardware is broken and you send somebody over to just check, or you figure out, hey, the heater is heating and the cooling goes on, and the heater is heating and the cooling goes on. So cyclic behavior in time series can also occur here in these settings. And you want to highlight these, not just work around them, but say, hey, maybe if we manage to get rid of this cyclic activity, we can save some more electricity. One more thing, yes, transfer to other buildings. At the moment, it looks like for every single building, we have to do everything from scratch again. In particular, that thermal model. And we don't have the thermal model in the first place. That's a really big problem. We may have some blueprints from many, many years ago, but that does not necessarily say what, well, it should mention somewhere what kind of materials are implemented here and there. But generating a thermal model maybe based on blueprints or JPEGs and GIF files or GIF files, that could be really helpful. I've seen some work on, I'm veering off into the wrong direction here. So creating thermal models is for sure, if people really catch on and they want to do much more building automation in the future, if you manage to generate thermal models somewhat automatically, that's going to be immensely helpful, because otherwise a person has to sit down and do this entirely by hand. Once you have that thermal model, you have to fine-tune it. How do you do that? I do not know. In principle, yes, we do have lots of data. We've got megabytes or gigabytes worth of data to play with it. But yeah, I don't know. We are not having much luck with the fine-tuning of the model once we have it. Maybe it's the quality of our sensor data that we have in the first place. But again, every single time for every single building, we would have to do this from scratch. One last thing I want to maybe mention for the reinforcement learning specialists amongst you. One interesting problem that we have here is that we start with systems that are set up, so these building automation systems that are set up with a particular fixed set of rules, and suddenly we start to change the rules. We have a reinforcement learning agent, and then you start to explore parts or see parts that you've never considered before. Maybe that's a well-known machine reinforcement learning problem, but essentially it's you're moving out of the envelope, you're pushing the envelope of what we are moving. You know, as an expert, what the building typically does, but suddenly you end up maybe turning some fans on or some ventilation on here, some cooling on there, some heating on there, which is a bit counterintuitive, but maybe it has to work. But these situations would never be, you wouldn't train them. It never occurs in your training data. Maybe that's not really a problem. Maybe it is, I don't know. I'm not a reinforcement learning expert. Yeah. It is also of interest to large companies, this building management system. Yeah, you will notice that in the next, well, still remaining maybe 30 minutes or so, I will never talk about related work. We have a rough idea of what's out there, of course, and one of the papers that's out there in that space is, for example, from, what was it, DeepMind, a few years ago, where they worked together, where they controlled intelligently, using some version of this, one of the office buildings and a shopping mall. And in that case, they saved about 9 to 13%. That's the number. These are the numbers that they were referring to. So if we can save, let's say, 10% of electricity with just a bit of software, I think that's pretty good. And as you can see, or could have seen beforehand, millions and millions of dollars are spent, in our case at least, on electricity each year. Why not save 10%? All right. I understand I've rushed a little bit through this, but this was case number one. So single building control, lots of challenges for us, where I also think because the building retrofit market is a multi-billion-dollar business, billions and billions of dollars. If you want to enter this, I think the hurdles are actually not that high. One of the biggest challenges is probably the access to data, in case you want to dabble in that space. Or maybe you collaborate with one of the big Honeywells and Siemens next over, so I may have Siemens. Or Schneider Electric or so. Yeah. All right, that's everything I want to mention here with respect to building control. Different project now. Power grids, power flows. So going away from a single building to lots of buildings. Before this presentation, sometime last week, I asked some colleagues, hey, do you have anything that I should maybe pitch on your behalf? And Taryn said, oh, yes, sure. So I believe that means, so I said I go here to a summer school where I'll be talking about machine learning opportunities in grid operations. And the response was, I believe that means you want any energy-related, grid-related problems that could benefit from auto-parameter tuning for ML models, right? In my understanding, if my understanding is correct, that would basically cover all problems, smiley face. So in his opinion, because he's been working in that space for a while, everything could benefit from a fair sprinkle of machine learning on top, automatic tuning. Just the problem is many of the colleagues that work that have more the electrical engineering background, they do not know the tools. So if you have a tool where with a press of a button, it does everything for you magically, okay, then I'm a bit exaggerating here, well, maybe not. It can have massive impacts outside of your communities. Talk to the people or see where the electrical engineers publish their papers and, well, kind of invade their space and say, hey, we have this problem here or maybe 10 problems. We use our magic toolbox, whatever the name might be, press the button and it does all the magic for you and you end up being better at a fraction of the cost. We did something like this maybe 12, 13 years ago with wind farm optimization, and these papers, as a computer scientist, they were not particularly exciting. But they were quite influential because we brought other technology into the area. Cool. All right. Again, there's going to be a lot here. I will simplify it a little bit. I will just say the following. Traditionally, say many, many years ago, 10, 20, 30, 40 years ago, power grids, electricity networks looked more like this. You have a couple of large generators, and electricity would flow from there out to the consumers. With all the integration of our solar panels and wind farms and our distributed energy resources, this is changing. In principle, it's good because we produce less CO2, but the bad thing is that suddenly you end up with a lot more power flow between many, many more, or sometimes bidirectional power flow between many more customers. In the morning, electricity might go left, in the evening, it might go right. Yeah. This causes problems if you want to optimize operations. You have many more consumers suddenly participating, and there was many more consumers and generators participating. You don't have enough time to do the optimal power flow calculations. And this gives rise to some ideas around decentralization. So instead of trying to, do operations or to calculate something for maybe 50,000, 100,000 customers, you break it down into your local grid, maybe for 10 or 100 users and consumers, and then you can tackle the problem again. But for that, you have to be able to locally, with potentially very limited computing power, find a solution. Why do you need to find solutions? So maybe I should briefly mention this here. In the first 15 or 20 minutes of my presentation here, I was very much worried about modeling in the first place, and then the reinforcement learning or so the optimization I wasn't really worried about. Here it's quite the opposite. Given a particular situation, I want to know, so I press a button and some technology should tell me, you generate this much, you generate this much, your solar panels produce too much, I have to curtail your output, I have to cut your output, and that wind farm over there is not, it's fantastic that we have it, but it's very intermittent, so we need to have solutions very quickly so that we don't overproduce. We don't always overproduce, it's not good for the grid, and it wastes the money. So now we want, given a particular situation, jump to a really good solution right away. In principle, not a very difficult problem. One challenge is, I'll skip over some parts. Yes, we do have a lot of data, but one challenge is, give me a second, that this end-to-end learning, if you just want to use some machine learning approach, is, so that's a 10 kilometer or 30,000 feet view, super simplified, is not really possible. There are lots of technical challenges, I'll have them in a moment. One of them is that your grid, so if you're trying to simulate the grid and you try to predict, you produce this much, you produce this much, and that battery should discharge, so that large-scale battery should discharge, and this gas generator should provide 10 megawatts of output, and here's the hydroelectric, or this pumped hydro storage that should maybe just pump some water up. So making this decision, in principle, is of course possible. I mean, the neural network will never complain, right? You hit enter, it spits out numbers. The problem is your architecture of your network can change. You have lots of line switching happening every single day. So the topology of your network can change every 5 minutes. Line switching is done in order to distribute electricity more efficiently, or sometimes you simply have the problem of a blackout, and then you need to confine it and redirect electricity. So you're underlying the electricity grid that you're simulating here, the topology can change, which is not fantastic, and as a consequence, all the flows suddenly, or some of the flows start to be different. Your price can vary throughout the day many times. Your battery kind of has a temporal aspect to it, so you need to consider the state of charge. I'll leave it at this for now, but I have a few more challenges here as well. So I'm pretty sure that components exist that can model each in isolation, but some of the big integration fails. And maybe there, again, architecture can be, if one were able to optimize over or create architectures that do everything for us, that would be incredibly helpful. Press a button, come back a week later or so, and then you have this architecture that does everything for you. One of the challenges with all these models is that they need to be, well, unfortunately, under the hood, there's a lot of physics happening when you have alternating current, and lots of nonlinearities. And this is not fantastic if you try to, apparently, when you try to solve it, and lots of equality constraints. And that's the big pain, apparently, for at least electrical engineers that want to do something in that space. The neural networks, when they spit something out, they don't always care very much about equality constraints. And why are equality constraints important? You cannot just produce electricity out of thin air, right? You've got, whatever, 2 megawatts arriving here, and then you send 1 megawatt left and not 15 to the right. That doesn't work. You have 2 megawatts coming in, 1 to the left, 1 to the right, for example. And as soon as you deviate from this prediction, or your entire solution becomes infeasible, because you're violating fundamental physical laws. So getting the physical understanding into there without exploding the runtime is really, really important. Of course, you can model nonlinear aspects all the time, just takes a little longer. And then you've got the temporal aspect again, that it just takes longer and, to execute the system, or to train it in the first place. A lot of work has been done in that space. Lots and lots of formulations that try to be faithful while being also computationally equivalent, computationally efficient. And you can still get really good papers at your A-star conferences, AAA and HCI, with just a modeling in this case. Super briefly on the data side, in principle, there's a lot of data. And we've got lots of different situations in our grids as well. So certain things happen at a 5-minute rate, at least in Australia. We've got certain other operations that happen, or calculations that happen at an hourly rate or daily rate or weekly rate. But within a smart grid, say locally, if I looked, let's assume Marius and I would be neighbors, if I would be producing some solar and electricity, and he has some spare capacity in his battery, he could have this, but if we can negotiate just every 5 minutes, it might not be okay. If at the same time, can't see any numbers here, names here, say at the same time, if Nick maybe wants to charge the EV, I need maybe a temporal resolution of maybe seconds. So something needs to calculate very quickly, which is not a big problem with lots of machine learning. But if I have to train it every 5 minutes or adjust it every 5 minutes, it might suddenly become very, very computationally costly. All right. What do some of the electrical engineers come up with, or the computer scientists that dabble in that space? They create architectures like this. This is, in my understanding, well, it's not really understandable. You've got some networks where the load goes in. Okay, that's in principle a nice idea, because load is your starting point. You know that Monash University is needing 5 megawatts, and there you've got a supermarket that needs something. So you've got your consumers, and you're trying to match the load, so all what's needed, with their generation. There's a wind farm over there, gas power plant over there, coal over there, and you're trying to come up with the best combination that saves the most money. So maybe as wind farm you don't really have under control, but your gas power plant you have under control, your coal power plant as well, and maybe some batteries. So what this particular architecture does is that apparently first they focus on just voltages, yeah, okay. Then angles between the phases, then some additional arrows, and they do the arrows twice, and you've got thermal bounds as well, and they just take them out of various levels, layers here and there, and he's got them in a AAA paper. Now this was for sure very difficult to set up, but I don't think it's not particularly intuitive. I had a look at the paper and it's still magic. Why is it so magic? Why can I not understand what's under the hood? And it's still not perfect, unfortunately. So, yeah, I find it a bit strange that why is there always some information taken out of middle layers and fed in later, but all these, the phase angles are important, the voltages are important. Why does it have to be something like this? Why can it not be, why is this worth, okay, that might not sound really bad. Why is this worth essentially a AAA paper? Why is it not possible to press a button once and let your cool technology generate something like this? There has to be some architecture that can achieve this as well, right? It's not magic. Well. All right. I will skip over the decentralization. This one thing I want to briefly mention is, yes, maybe this one here briefly. So Terence, that's my colleague, he's also working in that space a fair bit, or has been for quite a few years now. And for him, the violations are quite a big problem. So whenever you have a prediction error, sometimes this prediction error can essentially mean you're off by a few megawatt hours, or megawatts, yeah, megawatts, yeah. Well, here, 10, 30. So often the prediction is kind of, it generates the right prediction, right? It's the correct configuration. But here you've got sometimes 15 megawatts off 20 to 35 megawatts, just because of the learning. So on average, of course, you kind of are doing the right thing. But in practice, you can have many megawatts off. And if you're many megawatts off with your prediction, your network can go down. And you don't want that, for example. Or you're simply paying too much. So long story short, let me maybe focus here on the gray boxes here. What are maybe some interesting challenges for automating machine learning? Personally, I would find it fantastic if there would be some components in there that could sneak in the physics. Incredibly helpful. Not just for Terence, but for many other people out there. And there have been some works, what was it? AI Feynman or so I've seen a few years ago, and others that try to recreate this. But it is not quite the same. We are trying to rediscover the physics here, and a particular function like an acceleration of an apple or a remote that I just dropped down onto the ground. We don't try to reconstruct it, but we try to have it modeled somewhere and be computationally very fast. We do have the problem that we don't have all the data. So there are line losses, for example. You've got impedances, resistance on the lines. We don't have these values. So this we can only make up with training, with lots of data, and then hopefully adjust all the parameters along the way. We also don't quite know and this is all irrespective of any hyperparameter tuning that we might want to do along the way. So structure is really important, in my opinion, based on what Terence told me. We also don't quite know how to properly deal with constraints. One easy way of dealing with constraints is that you generate a solution first, and then you fix it. Okay, but then why do the machine learning in the first place if you have to fix it afterwards? That assumes that you can fix it easily, right? That's not a trivial thing here, constraints from what I know. So maybe those of you who focus a bit more on machine learning directly, on particular technologies there, help us get along with inequality constraints, especially equality constraints. Because we cannot, in electricity, not simply make things up out of thin air or make electricity go away. When it comes to our objectives, we also don't quite know what we actually want to go for. Do we take mean squared error, mean absolute error, or just the worst case error? Maybe worst case sounds okay, but then you lose the local sensitivity when you actually do your training. And if you don't just focus on the worst case, then you see the distribution from about 2 slides ago where you're suddenly 30 megawatts away from, well, what you should be doing. Not cool. Once you have this all in place, then you can go ahead and do lots of what-if analysis. You can press the button and say, okay, if the conditions are like this, here's going to be the optimal allocation here's your optimal allocation of essentially what this generator should produce and that generator should produce and how much this battery should feed into the net. That would be incredibly helpful for essentially energy markets around the world. Yeah. Because once you can do this, you can match supply and demand more effectively. You can determine the price, not necessarily, so you don't play with the price, but you can at least determine the price that everybody has to play. And this also means if electricity providers can do this in the first place, at home, they can pay attention to certain markets or signals from the market and say, hey, okay, it looks like maybe if I play forward a little bit, maybe 3 years, 5 years into the future, maybe I should be investing $100 million into a big battery because then it will become really interesting. But for that, you have to be able to solve all this AC OPF in the first place, because otherwise you might be 5, 10, 20% off. So you do need the accurate, very, very, very accurate predictions that are physically correct. Wow. Okay, cool. So that's all I want to say here about well, having a couple of systems work together to some extent here in a grid. Don't worry, the last case is going to be relatively high level. Very different setup. Don't worry, we are not talking too much about numbers now anymore. We're looking at humans and interacting with humans. Context here is climate change misinformation. I'll have some examples in the future, just on the next slide. This is important for us. So we want to discourage, or we want to detect when we have some questionable statements online, for example, and debunk them. So respond to them adequately and in a responsible manner. How do you do this? Well, this project started about 1.5 years ago, maybe 2 years ago, when ChatGPT came around, and it was so easy to just generate text, right? You ask something, you get text back. It was fantastic for us. Before that, we couldn't really do this, right? We could merely have maybe a classifier that takes text as inputs and say, okay, this is this part of logical fallacy or that fallacy or this kind of misinformation technique and so on. So a text-based classifier was no problem, but automatically generating a response, let's say 3 years ago, completely out of question. Categorization, classification, not a problem. Generating text, very difficult. Because we want to roll this out, deploy it, and have some impact and make the world, well, at least make some of our fellow citizens a bit cleverer. As an example, I hope you can kind of see this. Let's assume somebody says scientists are biased. Okay, this is now a piece of misinformation. Some of you might say, no, yes, that is misinformation, because we think that so at least in the context of climate scientists, so our understanding of climate science is supported by many scientists across the world, employing independent methodologies to come to robust, consistent conclusions. Okay, so the myth and the fact seem to be somehow a bit in conflict. That's a good starting point. Let's maybe ignore, okay, where do we get this from in the first place? But let's say this Google, okay, some search engine this week, or maybe the ChatGPT. By the way, whenever I say ChatGPT, it's just any large language model, okay? So maybe the large language model has an idea of, or the ChatGPT has an idea of what's happening. It is, when we want to respond to it, it's very helpful, so psychologically proven, if we can tell people, hey, what you just said is not only incorrect, but this is why it's incorrect. There's a particular fallacy that you're following. In this case here, it's ad hominem. It's an attack of a human. You're attacking people and not the science. So the fallacy explanation is you attack the scientists instead of engaging with their scientific research. That's how you could potentially debunk, respond to this piece of misinformation. Now this here by itself might not fit into a nice Twitter message. What do you do with this? Well, one of our colleagues, John Cook, is a psychologist, and according to his research, when you package it into a hamburger, we have that in a moment, when you structure it in a particular way, the information can actually stick. It helps the person that you're educating, and it might even vaccinate them to some extent, so that they in the future can detect this. What he suggested, and what some other people suggested, is the following. You briefly mentioned the facts. So in response to scientists are biased, you say, okay, here's a fact. Then you repeat the myth, just to tell the person again here the silly thing that he or she said. Then you say, okay, you're committing a particular type of fallacy. This is why it's wrong here in this case. And then you elaborate once more on the fact. And by packaging it this way, apparently it can actually stick and sit in your head for a while, and you may be able to, so the recipient might be able to, well, even educate others in the future. What do we have here? Yes. In the context of climate science, there are approximately 30 such categories of types of misinformation, and you can respond to them all in a particular way. So you can probably already start to see where the machine learning problems come up. One is detecting the right fallacy, and the next one is putting this hamburger together. It's really called it, or he called it a hamburger because you have the patties on the outside, the facts on the outside, you have the meat and the salad somewhere in the inside. And this hamburger apparently can really stick. Super briefly, just two more examples. Yes, that's right. To make it more, right, that was really important, I missed this here in the title. What is really important when you debunk is that your debunking is trustworthy. So first it's automatic, of course, because we might want to roll this out on Twitter and debunk 10,000 messages or so per day. So it has to be automatic, it has to be accurate, it has to be, what do we call this here, accountable, in the sense that it tells the person how it arrived at this conclusion, and it wants to be credible. And we're currently working on adding to the hamburger then, I don't know, a dash of ketchup or so. That's essentially the URL that says, hey, here on the United Nations page, you can actually see, here's some supporting information. Two more quick examples, just to give you an idea of what other fallacies are out there. Myth might be something like climate change is a religion. Okay, sounds wrong, but okay, how do you respond to this? You can, if Markus would, or to say, if I tell Markus, okay, climate change is a religion, how would you just, okay, he can hit me over the head, but how can you potentially educate me? And there are essentially ways of identifying what kind of problem there is, and in this case here, you can't really change, you can't really compare a, what do you call this, something evidence-based with a religion that is faith-based. Okay, that sounds a lot more waterproof now to me. I can still decide to ignore it, but that's a different story. Very last one, you might have people saying, so again, there are about 30, don't worry, we will not go through all the 30. Another example could be something like, hey, solving climate change is too hard, so why bother? But then you say, hey, by the way, there are actually lots of people that say it is actually possible. So what you start off with is an oversimplification, you address it, you provide evidence, and hopefully it sticks. There's no guarantee, of course. So what are we optimizing here for? What is our machine learning problem? Well, lots of things. And I will just talk you through 1 or 2 points here. We've been working on this for a little while, and we've had so many clever ideas, and we had to discard a good couple of ideas because ChatGPT got better. We noticed over the years that we could achieve a lot with prompt engineering, and then we had to work on the prompt engineering because certain models would stick to our instructions and, for example, produce the hamburger. Some others would just gobble things up and not produce hamburgers. So we need something that produces hamburgers reliably. Because as soon as we create we let a bot out, and if there are maybe 100 messages that are unreasonable, we're in big trouble, because then other people that climate change deniers, they will just say, hey, Markus and his team have done a shitty job. Look at all these debunkings, they're all rubbish. So we have to be very, very careful here. We've done some model tuning just to improve, we've checked lots of models, we've done lots of tuning of some parameters here. We've created so many different architectures that helped us maybe first to identify the right fallacy, and then create debunking, sometimes even tuned differently for different types of fallacies. And it's not easy, it's really not easy. Long story short, because we worked so much on, we put together all these different architectures, I would again love to have something that is a bit more automatic, so that we wouldn't have, well, model selection and tuning, easy, done, right? Essentially, you all have the technology for this. But architecture-wise here in this case, we have one model first that classifies it, and then we have a specialized model on the left, a specialized model on the right, and every time we have different tunings there. It is a big mess. Of course, it works. Your F1 score goes up. Yeah. So what's our current status here? We have a good number of things under control, so the detection works reasonably well. I think we had something like, I'm not sure whether you can really say this, so there was some state-of-the-art beforehand, F1 score of 0.2 maybe, and we achieved 0.7. Not fantastic yet, but at least almost an order of magnitude better, or half an order of magnitude better. So we're much, much happier with this. We are still working very much on getting the right facts into the hamburgers, and we want to deploy it, of course, at some point. So have it being deployed, responding to people online. There are some ethical challenges there. Yeah. Where you can maybe help us, if you want to in the future, is on that system structure, because we jumped around so much. I've tried to put that slide together yesterday, and at some point I lost it because I wasn't really sure what system we are working on anymore. We do have a fair sprinkle of tuning, fine-tuning models. We'd like to put, just so for fine-tuning models, we also would like to just, have some more building blocks that we can incorporate. So it's for example, using the internet as a building block, using a particular data set with particularly outstanding examples to feed it into the responses. So there's lots that's still possible here. Yeah, there was one more thing. Yes. And we are trying to work an almost GAN-style approach where another network essentially tries to evaluate how good are the responses. And this is surprisingly difficult for us to say. So before we release it, we need a quick sanity check. Okay, is the response that ChatGPT has put together actually reasonable? And it is very costly to think about a statement, identify it, and write the hamburger yourself. So that's currently a bit of a challenge for us, how to automatically critique what we actually generate without having to roll it out to 1,000 people or 10,000 people right away. So long story short, there's a lot happening, at least in Monash, in the energy space, ranging from model predictive control to modeling something really accurately to the dot of the I and so on. Architecture is a big challenge for us because we don't have the right tools for this. Architecture search, putting together the right components, a fair sprinkle of parameter tuning is always helpful because at the moment our students still do this by hand, which is not fantastic. Yeah. So that's it. So lots and lots of opportunities here. Lots of money can be saved, and if you work in that space, you can make the world a better place and save money and CO2 and so on.